Welcome back to GLS4OM. We're continuing our foray into Unit 7, Techniques of Integration. Last lesson we covered integration by parts. Finished with a little video. I hope you found that video. That group of people singing about integration by parts. Continuing with our humor of the day. This is sort of an extension of the humor we had last time from binary numbers. So this is new classic fiction with binary numbers. I'll just leave this up for a few seconds. And then if you want to figure out what they're saying, you could pause the video and work your way through it. Just a reminder that in binary numbers 1, 2, 4, 8, 16, 32, and so on. And it's either turned into an on state or an off state. So if we had 0, 1, 1, 0, this is how you'd write the number 6. 0 times 1 plus 1 times 2 plus 1 times 4. That's how you write the number 6. So you should be able to figure out what these are. A different look at humor today. Why did the chicken cross the Mobius strip? So why did the chicken cross the Mobius strip? And the answer is to get to the same side. And if you don't know what a Mobius strip is, you can take, say, like a piece of paper, the length of a ribbon, put one twist in it, join it together with a piece of tape, and then if you take a pencil and trace, you will see you can trace around the whole entire thing. It just becomes a one-sided strip. So a Mobius strip is actually a one-sided strip. So I found this little comic. It seems like I've seen this joke before because, of course, this is a Mobius strip. Notice that long piece of paper with one twist in it, and it just becomes a one-sided object. All right, moving forward. There's a bit of a spoiler alert. These are some questions from the performance task. I would like you to think about, this is integration by parts, and I'm getting you to decide what you think should be U, what you think should be DV. So in this particular case, what do you want to pick for U, what do you want to pick for DV? And remember, it was using the rules of Liate, they said in that video, but I was calling it Liate. Who knows how to pronounce that for sure? So it's a time to ponder, pause. What do you think should be U? What do you think should be DV? And returning and resuming. So according to the rules of Liate, the algebraic function comes before the exponential, so you should be allowing U to be 2x plus 9, and then you would allow dV to be e to the x dx. And then moving forward, du would be 2dx, and v would be e to the x. And we're looking at the integral of u dv is equal to uv minus the integral of v du. So integration by parts allows you to take one integral and write it in terms of a product and a second integral, and the objective was to make the second integral simpler than where you started. And notice this integrand is right here, and when we do this, our new integrand is going to become 2e to the x. In this case, this is the algebraic function, but this is now a log function, and the log function is further to the left in the word liate or liati. So u is going to be ln of x, dv is going to be x to the negative 5 dx, and taking the derivative of this one we get to here, the antiderivative of this one we get to here, and notice when you multiply these two together you're just going to get an algebraic piece. You've lost the log piece in your integrand. Alright, again, spoiler alert for your performance task. 2 more for you to think about. So in these particular questions, what should be U, what should be DV? And once again, a time to ponder, pause. Alright, and then just finishing this up. So if we take a look, we have a trig function, or a product of 2 trig functions. It looks like there's 2 trig functions in here, so it looks like we're a product of 3 things. But it turns out when you continue, you allow your algebraic function to be u, and you allow the trig pieces to be dv. This, when you go backwards, that was just the derivative of secant x. And when you go forward on this, you get du equals dx. And your new integrand is just going to become this. which is much simpler than where you were here. And on this particular one, we're taking a look at this. It doesn't look like we have a lot of pieces here again. We've got this, but this is an inverse trig function. So that would be our second letter in the world of Lyautey. So we should allow this to be u, and this is really our algebraic piece. I'm going to put 1 dx there, because when you go backwards on this algebraic function, you're going to get x. And when you go forward and you take the derivative of this, you get 1 over the square root of 1 minus x squared, and then you can move forward from there and finish this particular question off. All right, so what are we going to learn today? What's new? So what we're going to look at today are integrals involving powers of sinusoidal functions. So let's take a look at this a little bit right here. I'm just noting what I'm telling you up here. We do have a product of power functions of sinusoidal functions. So sine to some exponent x times cos to some exponent x. The decision on what to do is actually going to depend upon whether m and n are even or odd. Noting Pythagorean identity number 1, sine squared plus cos squared is 1, so maybe we want to make this substitution. Or maybe we want to make that substitution. It's also possible to use double angle formulas. Cos of 2x is 1 minus sine squared x. So then a sine squared x could be replaced with, if I isolate this, I will get 2 sine squared on this side. I will get 1 minus cos 2x, and then I divide by 2. So it's possible we might want to use that substitution for a sine squared. Or isolating this one for cos squared, getting cos 2x plus 1, divide that by 2. We might want to make that substitution for cos squared. All right, so moving forward, we also might want to make use of some reduction formulas for sine and cosine. So the reduction formula for sine is, here's an integral. It's written in terms of a product and this other integral. We have this integral for cosine, and it's written in terms of a product and another integral. What does this remind you of? I'm going to give you a few seconds to think about this. What does this look like to you? We have an integral written in terms of a product and another integral. That makes me think about integration by parts. So we're going to move forward, and what I'm going to attempt to do is I'm going to walk you through a proof of this. How did we determine that the integral of sine to some exponent n x dx would be equal to negative 1 over n sine, we've taken 1 off the exponent, x times cos of x, n minus 1 divided by n, and an integral where we've taken it down. Now the reason this is called a reduction formula is because it's bringing the degree down. And you could apply the reduction formula several times if you started something, say you started with something sine to the degree 8. Then you could apply this one. You would bring the integral down to degree 6, and then you'd apply it again on this piece, bring it down to degree 4, apply it on this piece again, down to degree 2, and then one more time and you'd be done. So you can use these reduction formulas multiple times. All right, so taking a look at the proof of this. So I saw integration by parts here. And in order to get integration by parts to work, and you're looking for a clue, you know that this would be u, and then we would have a v here, right? We'd have a u and we'd have a v. And then we'd have a v du. So I took my inspiration from here in deciding how to split this up. So sine the exponent n minus 1x times sine x dx. That's going to allow me to choose u to be sine to the n minus 1 of x. And then v is going to be negative cos x. I'm going to take the negative and associate it with the cos x. That will give me dv as sine x. Moving forward on this, I'll get n minus 1. Sine to the n minus 2 of x times cos of x dx is now my du. So breaking these apart, I now have, there's uv, minus the integral of v du. And if I'm going to clean this up a bit, a negative times a negative becomes plus. So now we're out to here. So we're close to what we need. We've got this little bit so far. But now in here we have cos squared x times n minus 1 times sine to the n minus 2 of x. So the next bit I said was I got to get rid of this because we don't see a cos in there. So I can replace cos squared with 1 minus sine squared. That's where that came from. And then what I'm going to do next is an expansion. Expand this through here. Nothing else is changing on these lines as we go through here. So this times this becomes sine to the n minus 2 of x. Minus this one times this just becomes minus sine to the exponent n of x. And that whole thing is being multiplied by n minus 1. And now the next thing we're going to take a look at is there are linearity properties of integrals. So now I can split this into two integrals. This one times this piece is one integral. Then this times this piece, so minus n minus 1 times sine to the n, or the integral of sine to the n of x dx. So again, properties of linearity of integrals allow me to split this into two integrals. And then the next little bit, what I'm going to do is I'm going to take this to this side. I'm going to bring it to the other side because it's the same integral as this. So this is very similar to the integration by parts you did on an exponential with a trig. And I said you have to do integration by parts on that one. You did it twice, and then you ended up with a common integral. So we do have a common integral. Bring this to the other side of the integral, and we get sine, the integral of sine to the n dx, plus n minus 1, the integral of sine to the n of x dx. And the other pieces are staying the same. That's still written here, and then that piece is still there. Now what I have here is really 1 plus n minus 1 sine to the n dx's. And so that's just going to simplify to give me n times sine to the n. Oh, we're missing an x on these all the way along. That was sloppy writing. So let me put that back in. There should be x's on all of these. Put that one there. Put that one there. So now we have n times sine to the n of x dx equals negative sine n minus 1 x cos x plus n minus 1, the integral of sine the n minus 2 x dx. Very, very close to what we need here. And now if we just divide this by n, I can get from here back up to there. So this reduction formula came by applying integration by parts on this. So if you have time, what I'm going to suggest you do is use integration by parts on this one. See if you can figure out what should be u and what should be dv. Take inspiration from what we're seeing here and see if you can derive that reduction formula. All right, moving forward. Trigonometric integrals. So I'm just going to pause for a moment. All right, we're back. Trigonometric integrals. So I said we're going to have a product of powers of two trig functions. N and n are either even or odd positive integers. So what we're going to take a look at is if m is odd, just m is odd, then what we will do is we'll change all but one of the signs into cosines using this. So if I had sine to the power 5, I'd be looking at a sine to the power 4. I'm still having trouble writing on the trackpad, but this is the best I can do. I haven't found a way to attach my iPad to this effectively yet. Squeeze our x in, squeeze our x in. So it's saying if m is odd, then split it. Take one extra x out, and now you're going to have an even. This even bit could be rewritten as 1 minus cos squared, and then I'd have to square that twice, because, not square it twice, but just once, because we have sine squared x, all squared, times sine x. So that'll be possible. Every time you have an odd exponent, you can simply take one sign out, and then you could raise this, whatever would be left. If it would be 6, then I divide that by 2, and then I'd be writing sine squared all cubed. And then the substitution you're going to make is you're going to allow u to be cos x, because then your derivative, you would get negative du is sine x, and that's how you're going to get rid of this piece. If n is odd, we're going to do the same idea. We're going to change all but one of the cosines into sines. Using cos squared as 1 minus sine squared, we'll make this substitution u is sine x, and then du would be cos x dx. If both of them are odd, then you can make either of these substitutions. The harder bit is when they are both even. That's a bit more work. because then we'd have to use the double angle formulas. So let's back her up so we can see where those double angle formulas were. The double angle formulas were right here. When they're both even, we're going to make these substitutions. Every time you make one of these substitutions, you take the degree down by 1. All right, so now I'm going to walk you through maybe a couple of worked examples, and then I'll get you to try one on your own. So we had sine cubed. And they said, how do you handle it when it's a sine cubed? You can break this up into, we could also use a reduction formula on this one. So I'm just going to jump, later on I'll show you the reduction formula. I tend to, on these particular ones, use this reduction formula. When you have only one trig function, when you don't have a product of two, I like it. I like better, I prefer actually, that's the word I should say. I prefer to use the reduction formulas, but I didn't in this case. If you don't want to use a reduction formula, what you're going to do is something different from what I had stated. We're going to break this up into a sine squared, and then I'm going to write that as 1 minus cos squared, because then I can make the substitution u equals cos x. Again, that was not covered as one of our possible cases here. Because the cases we were covering was a product of two trig functions. These guys here that I'm mentioning here only work when you have both a sine and a cosine. So jumping back over here and working our way through this. We break this up into sine squared times sine x. We're going to write this as 1 minus cos squared times sine x. The substitution I'm going to make is u is equal to cos x, then du is negative sine x dx, so negative du is sine x. So there's the negative, there's the du. This becomes 1 minus u squared. And then if we go backwards on this, the antiderivative of 1 would become u. The antiderivative of negative u squared would be u cubed over 3. And then if we distribute, don't forget the plus c, of course, and if we distribute, we will get positive u cubed over 3 minus u plus c, and then back substituting our cos x, we get cos cubed x over 3 minus cos x plus c. All right, this one is missing an x as well. Let me put that back in there. So now let's take a look at the next example when we have a product of 2. So we're going to target, we have an odd exponent here, so let's target that odd exponent. We're now going to write this as sine to the 4th x times cos to the 4th x. Take out all of the, well, we've taken out the extra cos. That's all, I'll word it this way. We've taken out the extra cos. That left a cos to the power 4. Cos to the power 4 can be cos squared, all squared. So that's why I've written this as 1 minus sine squared x all squared. Substitution we're now going to make is we're going to allow u to be sine x. Then du would be cos x dx. So this bit is going to become du. I will replace this with u. That becomes u to the power 4. Replacing that with u, that becomes 1 minus u squared all squared. And now we're going to work with these algebraic functions. So u to the 4th, expanding, we get 1 minus 2u all squared, plus 4u to the 4th, and then distributing, we'll get u to the 4th minus 2u to the 6th, plus 4u to the 8th. And now we're ready to go backwards on these algebraic functions. So this becomes u to the 5th over 5, minus 2u to the 7th over 7, plus 4u to the 9 over 9, plus c. And then back substituting, replacing within this algebraic function, substituting our trig function. So sine to the 5th x over 5 minus 2 sine to the 7th x over 7 plus 4 sine to the 9th of x all over 9. So what we're doing is we're noting these are really an algebra of trig functions, and when we make these substitutions we change it purely into an algebraic function. It's very easy to go backwards and take the antiderivative of these algebraic functions, especially when they're written to a power, and then that gets us down to there. All right, let's look at one more. One in which they're both even. And thankfully this was a low value. I mean, I would not want to be doing sine to the 10x times cos to the 12. of x. I'm just showing you how the technique works. That's supposed to be a 12. This would be a lot of work. I'm going to walk you through the technique. So what we're going to do is we're going to take the sine squared. And I'm just going to draw your attention back over to this one. I'm going to replace sine squared with 1/2 1 minus cos 2x. I'm going to replace the cos squared with 1/2 times 1 plus cos 2x. Where did they come from? The double angle formula. And if you isolate the double angle formula for a sine squared of x, you can take something that has degree 2 and replace it with a trig function that has 1 degree less. So this is, in effect, a reduction. It's reducing something. The reduction formulas we have over here only apply when you have a single trig function. It doesn't work on a power or a product of two trig functions. So coming back over here, I have replaced sine squared x with 1 minus cos 2x all over 2, but I chose to square them in separate pieces. Square the 1/2, 1 minus cos 2x all squared. I'm now going to replace the cos squared of x with 1/2 1 plus cos 2x dx. Squaring 1/2, we get a quarter, times this 1/2, I get an eighth. Expanding here, I get 1 minus 2 cos 2x plus cos squared 2x, and then leaving that piece alone. And then another expansion. So if you do this, what do we have here? A trinomial times a binomial, you'll end up getting to here. 1 minus cos 2x minus cos squared 2x plus cos cubed of 2x dx. And again, linearity property of integrals will give us, instead of the integral of 4 pieces, we'll take 4 separate integrals. So we have the integral of 1 dx minus the integral of cos 2x dx minus 1/8 the integral of cos squared 2x dx plus 1/8 the integral of cos cubed 2x dx. And then I made this substitution. Replace u with 2x, and then du is equal to 2 dx, just to make taking antiderivatives easier. Obviously, I didn't do it in this case here because it's simple to go back on 1. That's an algebraic function 1. The antiderivative of 1 would be x. So that became 1/8 x. But now I'm making this substitution, and remember du over 2 is going to be dx. So when du over 2 is dx, every one of these eighths will have to switch to a 16th. Nothing else has changed other than replacing, whoops, we dropped the u again. That should be cos of u du, cos squared u du, cos cubed u du. And then moving forward. So we now have minus 1/16 the integral of cos u du. And then what are we going to do here? What are we replacing cos squared with? Pause for a second. All right, resuming. I didn't realize I had already pasted this down here. I wanted you to see, whoops. I'm going to make that a bit larger. Just wanted you to see where I went from here. So where I went with this guy is to one of the reduction formulas, and again, so much written on the page I didn't notice that I had already pasted it down here. So using a reduction formula, cos squared could be replaced with 1 over n. That's going to be 1 over 2. Cos to the n minus 1, 2 minus 1 is 1, so we'll get cos of u times sine of u. And now a new integral plus cos squared, so 2 minus 1, all over 2 is 1/2. That's where the 1/2 comes from. And if we do cos to the 2 minus 2, we get cos to the 0 of x, which of course is just 1 dx. So that becomes a du here. And now if you're going to use a reduction formula on cos cubed, what will happen? You're going to plug a 3 in here. You're going to get 3 minus 1 is 2. So we're 1/3 cos squared u times sine of u plus 3 minus 1 is 2, all over 3. That's where the 2/3 comes from. And then cos 3 minus 2 becomes 1, plus the integral of cos u du. So these two, once I got to here, I used a reduction formula on these two. And so now cleaning up a bit. This one I felt I'm ready to go backwards on. So that's minus 1/16 sine u. Minus 1 over 32 cos u du. And then we have minus 1 over 32. I can go backwards on this. That's straightforward. That's a 1. Going backwards on that, I get a u, plus 1 over 48 cos squared u times sine of u. And then going backwards on this one, we have what, 2 over 48, that becomes 1 over 24. And going backwards, the antiderivative of cos u is sine u. So 1 over 24 sine u plus c. And then trying to gather like terms, although I didn't simplify these two. After we do a back substitution, plug in a 2x, plug in your 2x, your 2x, plug in a 2x, plug in a 2x, plug in a 2x, and these two here were like terms, so I then could have simplified this to 1 over 16x. All right, then it's going to be time for you to do some practice. Again, I'm just going to do a quick summary. What are we looking at? We're looking at a product of power functions of sines and cosines. We want to use the Pythagorean identities, and we can use the double angle formulas as well, especially if we have a product in which we have two even exponents here. Then there were the reduction formulas, and the reduction formulas could be proven using integration by parts. Now, if this was university, I am positive these reduction formulas are going to be given to you. They tend to give you a lot of trig stuff. Even if we don't do a final assessment, I will send you copies of the exams used at Waterloo, Guelph, and I think I have a UT one as well. And you'll see they do have a lot of pages on an exam involving trig identities, trig formulas, etc. So I'm pretty sure the reduction formulas would be on there. And then it's just a matter of you deciding whether even or odd. Take the one that's odd, let's say m was odd, and you take out the extra sign, and then you replace based on the Pythagorean identity. If they're both odd, it doesn't matter. It's when they're both even that is the most amount of work, such as in this example here. So hopefully you'll get one in which one of the pieces is odd. So I'm going to allow you to work on this one. Word of caution though, now I've gone from an indefinite to a definite integral, so please make sure you change your bounds of integration when you go through this. And in this particular case, you've been given a power that is odd, so remember that's the place that you want to break that one up. All right, it's a time to ponder pause. All right, resuming, I'm going to break this up into cos squared times cos, and then we're going to replace the cos squared with a sine squared and make our substitution based on sine of x. So breaking this up into cos x times cos squared x, replacing the cos squared x with 1 minus sine squared takes me to here. I haven't changed the bounds of integration yet. Now I'm ready for a substitution. U is going to be sine x, so du is cos x dx. So this bit and this bit is going to become my du. This is going to become 1 minus u squared. That's going to become u to the 4th. That's how I got to here. Now I have to change the bounds of integration. So the lower bound of integration would be sine of 0, which of course is 0. The upper bound of integration would be sine of pi over 2, which is 1. I've now changed the bounds of integration to 0 to 1. Expanding, I get u to the 4th minus u to the 6th. And now we're ready to go backwards on those algebraic functions. That's u to the 5th over 5 minus u to the 7 over 7. Evaluating now across the bounds of integration from 0 to 1. We get 1 to the 5th minus 1 to the 5th over 5 minus 1 to the 7th over 7. Of course, I didn't bother to write in the minus zeros, but I knew they would be there. Common denominator, 7 over 35 minus 5 over 35, which becomes 2 over 35. So quite a little nifty technique. This looks rather complicated, but doing, I guess it's a substitution with a trig integral. I'm not sure how I want to describe this. It's not really the method of substitution. It's similar to the method of substitution. I guess it is very similar to the method of substitution from Unit 6, but we just trying to set this up so we get the derivative of the baby. We have to clean it up though. So there is the derivative of the baby, and these really were power functions. So I guess it is much like the method of substitution from Unit 6. All right, another one to look at. How are you going to handle this one? This is the integral of sine to the power 4 of x dx. And again, I think it's a time to ponder pause. All right, so the approach, let's take this one. The approach I took on this one was just to use a reduction formula. This time I remembered I have the reduction formula pasted onto the bottom here. And then I'm going to show you a different approach. We'll see which one you like better. So based on the reduction formula, n is 4. So plugging into here we'd be minus 1 over 4. 4 minus 1 becomes 3. So I plugged it right in to here. There's the cosx plus 4 minus 1 over 4 sine to the 4 minus 2. That becomes minus 1/4 sine cubed cosx plus 3/4 sine squared. And then what I decided to do now is I'm just going to apply the reduction formula a second time. So applying the reduction formula a second time, minus 1/2 sine to the 2 minus 1 x times cosx plus 2 minus 1 over 2, the integral of sine to the 2 minus 2 x dx. So sort of like in the very beginning I said, just keep applying the reduction formulas when you have just a single power of a single trig function here. You can just keep applying the reduction formula. And now I'm going to distribute minus 3 over 8. This becomes sine x cosx plus, this will be 1/2 times that becomes plus 3 over 8. That becomes sine to the 0, which is just 1. I didn't bother to write the 1, but I know it's there. And now we have minus 1/4 sine cubed x cosx minus 3/8 sine x cosx plus 3/8 if we go backwards on this one, x plus c. Note I wrote the plus c on this line, not on this line, because I didn't evaluate this integral until the very bottom line. So this one was done using reduction formulas. Now I'm going to show you an alternate approach. So this approach is using the technique that I outlined earlier, where we're going to use the double angle formulas. So I'm going to replace this with 1/2 1 minus cos 2x. I'm going to replace that with 1 minus cos 2x, multiply by 1/2. The quarter comes out in front, I distribute here, and now I have the integral of dx minus 1/2 the integral of cos 2x plus 1/4 the integral of cos squared 2x dx. And then continuing forward, I just went backwards on that one right away. That's minus 1/2 sine of 2x over 2. This one I did a bit of a substitution. And then evaluating this one using, in this particular case, what I used there was a reduction formula. And then I got down to here, this little piece here, and then I have this little piece here. And the question is, are those the same thing? So I'm going to bring you over to here just to show you. They were indeed the same things. So this was the work I was working on earlier, just to show you. Let me turn these ones off. And that one as well. Whoops. So you can use Desmos as a check to make sure you are correct. So using the reduction formulas, let's just take a look. When I use the reduction formulas, I got this one. When I used the other technique, let's see if I can find that one. There. When I used the other technique, I got this formula right here. Are they the exact same answer? And if so, how could we move from one to the other? So we're just going to show you here. This is the one I got from the reduction formulas. And this was the one I got, I think it was that one right there. That was the one I got using the technique with the double angle formulas. And the question was, are they the same thing? Well, we can see graphically they are here. Now, all of these other functions were my attempt to go from here to there, just to prove, it's like proving a trig identity, right? So what I'm going to do is I'm going to give you some time to think about, can you go from this, which is the formula I get using solely reduction formulas, to the formula I got here by using the double angle formulas. Can you show that those two are equal to each other? That's a bit of a challenge. So I'm going to create a time to ponder pause now to see if you can do that. This is like proving a trig identity. All right, so taking this up, I felt it would be easier to start with a 1 where I use the reduction formulas. And what I want to do here is I need a sine of 2x. So how can I create a sine of 2x? So I'm going to grab a sine x and a cos x out of there, and then I'm going to leave the cos squared. And then I'm going to rewrite negative a quarter as negative 2 over 8, because this piece here becomes sine of 2x. That's how I got to there. Then I said, well, I'm going to try that same thing on this piece over here, right? And so I'm going to need to rewrite negative 3 over 8 as negative 3 over 16, and there's times that 2. That will reduce me back to 3/8. That becomes sine of 2x. I'm going to leave that piece alone, and I'm going to leave that piece alone. And then what happened in our formula, just jump you back to here quickly, we need a minus 1/4 sine 2x. So let me split this up into minus a quarter sine 2x, and then minus 1/4 or minus 1/8 sine of 2x. And then taking a look at this little bit over here, I'm just going to pause for a sec. All right, never mind, I see what's going on. That's a typo on this line. Negative a quarter plus a 16th. This is negative 4/4 plus 1/16 is negative 3/16. So this was wrong. That said plus 1/8. That should say plus 1/16 because I need to get back to here. Actually, it said minus 1/8, but it should say plus 1/16. So let's cross this line off. That line's wrong. This line is correct. So we split those two. And then what I'm going to note is I can factor a sine 2x out of here, out of these two. And I'm also going to factor out a negative 1 over 16. So if we factor out negative 1 over 16, we will be left with 2 sine squared x on this piece. And on this one, we will be left with minus 1. And 2 sine squared x minus 1 is actually negative cos 2x. Cos 2x is 1 minus 2 sine squared. So 2 sine squared minus 1 is negative cos 2x. A negative times a negative becomes our positive there. And actually, I still left it as a negative times a negative, but it's going to become a positive eventually. Now what I want to do is, see how I have a sine 2x and I have a cos 2x? If I can get a 2 in front of that, I would now have sine of 4x. So to bring the 2 out in front, I'm going to rewrite this as 1 over 32. It now becomes 2 sine 2x cos 2x. I'm just going to make those pluses now. I should have done that earlier. Now this is the double angle formula for sine. So 2 sine x cos x becomes sine of 2x. In this case, our angle is 2x. So this is going to become sine of 4x. And that is how I get back to the other piece. So interesting look on how to prove a trig identity. So using the reduction formula and using the technique I outlined, they both give you antiderivatives, but not surprisingly, because this is trig and there's lots of ways to write things, they look entirely different, but you can go from one to the other. All right, one last question for you to work on. So let's see if you can use this identity to derive this as a formula for the integral of sine mx sine nx. And again, a time to ponder pause. All right, let's take this last one up. So I'm going to start with the integral of sine mx sine nx dx. Plugging straight into here, I'm going to get 1/2 the integral of my angles a and b are mx and nx. So mx minus nx minus cos of mx plus nx. And what I'm going to do now is I'm going to factor out the x. So this becomes cos of m minus n times x minus cos of m plus nx dx. Again, linearity property of integrals. I can split this into two integrals, 1/2 cos m minus nx dx minus 1/2 cos of m plus nx dx. And now I'm going to take the antiderivative. The antiderivative of cos is sine, but in this particular case, because it's not straight sine of x, it's really sine of, let's call it bx. So when I go backwards, I'm going to have to divide by b, because when I use the chain rule and take the derivative of the baby, I'm going to have to be able to get rid of that. I'm going to need b over b to become 1. So I'm going to have to do sine of m minus n times x, all divided by m minus n, minus 1/2 times sine of m plus nx, all divided by m plus n. And now we can simply associate the two here. Instead of seeing these as a product of two separate fractions, we will now multiply the denominators and leave this as sine m minus n times x, or sine of m minus n of x. Maybe it would have been better if I wrote it that way. I mean, that's exactly how Desmos would tell me to write this, to make it clear. The argument is the whole entire thing. So sine of m minus n times x, all divided by 2 times m minus n. Sine of m plus n times x, all divided by 2 times m plus n plus c. So we were then able to prove this. And I'll let you think about why does it say that m cannot be equal to positive or negative n. All right, that ends this lesson. It turns out it ended up being rather lengthy. It's really hard to do these lessons when no one is in front of you because you're never sure how much detail you should provide, what's too much and what's not enough. Anyways, hopefully you followed along with what we're doing. These were the key ideas for this particular thing. And again, we're looking for power functions of a product of power functions, powers of trig functions. So hopefully you found this video useful. Once again, if you made it to the end, thank you for watching, and don't forget to like and subscribe. Take care and be safe.